let's talk about some mathematical tools, how we can describe an enzyme catalyzed reaction. This tool is called Michaelis Menten equation to recognize the work by those two scientists who first actually did that, described the enzyme catalyzed reaction. And I just wanted to note that we will use this equation for all enzymatic reactions that we encounter in the course, but it's not necessarily true that enzymes obey, all enzymes obey Michaelis Menten kinetics. In order for us to derive this equation, we need to focus on what is going on, right, when this enzyme catalyzes conversion of substrate S into the product P. So first, substrate needs to be bound in the active site of the enzyme to form enzyme-substrate complex. And this process is at equilibrium, right? So formation of the complex is characterized by the rate constant K1. Decomposition can be back into free enzyme and substrate, characterized by the rate constant K minus 1, or the substrate in the complex can be converted into the product, and the product is released to regenerate the free enzyme. This process is characterized by K2. Now, the velocity of this process can be described as change in product concentration over time. And this one is, because we have this first order reaction, this rate will be proportional to the concentration of the enzyme substrate complex. How do we determine the concentration of the enzyme substrate complex? Because we cannot write the equation for velocity without knowing how this parameter depends on other concentrations and other rate constants. For that, we need to focus on actually the change in the enzyme substrate complex over time. And because this complex is formed via that second order reaction, the first term in this equation would be positive, K1 by enzyme and by substrate concentration. Now the second term, the second and third, it will be decomposition of enzyme substrate complex via first order reactions. The first order reaction will be decomposing the complex back into enzyme and substrate. So we have K minus 1 over ES. And the second will be minus K2 over ES. Okay, so here we already have ES, right, the concentration of the enzyme substrate complex, but we still have here concentration of free enzyme and free substrate. So if we assume that initial substrate concentration is much greater than the enzyme concentration, we can say that over the course, it will be the same as our assumption for the first order reaction, pseudo first order reaction, right? We can assume that over the course of this transformation, most of the substrate remained intact, not bound to the enzyme, right? So that allows us to say that substrate concentration is equal to the initial one. So we can just put that note right here. How about the enzyme? So the enzyme concentration is like initial one, is split into the concentration of free enzyme, enzyme substrate complex, right? And yeah, so here, because otherwise here we will need to take into account product concentration, we assume that product concentration is almost negligible, right? So we are talking about the very beginning of the reaction. Okay, going back to the enzyme. So here we have this equation for the enzyme concentration, and from this equation we can actually derive concentration of free enzyme as the original concentration minus concentration of the enzyme substrate complex, and that we can plug right here. So when we plug it right here, what we have is K1 over by the initial enzyme concentration minus concentration of the enzyme substrate complex by substrate concentration. And we can just leave it right here. The second term without changes and the third term. Now, if we follow distributive property, we will see that this term splits into two terms. One term doesn't depend on the concentration of enzyme-substrate complex, but the second term does depend. And now we can factor out the enzyme-substrate concentration. So we have K1 by E naught, S naught. And here we have minus ES. And in the parentheses, it will be K1 by the initial substrate concentration plus K minus 1 plus K2. Okay, so now we have assumption of equilibrium. Assumption of equilibrium tells us that the same amount of enzyme-substrate complex that was formed through those reactions gets decomposed either back into enzyme and substrate or forward into enzyme and product. So that tells us that concentration of enzyme-substrate complex doesn't change. So we can make this ratio 0. And so if we do so, we can solve this equation for enzyme substrate concentration, which is K1 by original enzyme concentration by original substrate concentration over K1 by substrate concentration plus K minus 1 plus K2. And we can further rearrange this equation by getting rid of K1 in the numerator. That will be if we divide both numerator and denominator by K1. So we have E naught by S naught over S naught plus K minus 1 plus K2 over K1. So this is here is actually called, it is defined as capital K M, and we call it Michaelis Menten constant. Okay? So now if we just put Km instead of that ratio of the constants and we go back to that original velocity equation, this gives us Michaelis Menten equation. So you can see that if we plot velocity as a function of substrate concentration, velocity will follow this hyperbolic function with some limit here, so it will approach maximal velocity. So when are we going to have that maximal velocity? We are going to have this maximal velocity when all enzyme that we have, right, is converted to the enzyme substrate complex, right? Oh, actually, not all enzyme. Sorry about that. It will be when pretty much. Okay, let's go back to first understand something. So when we have, oh yeah. Actually, we can explain it like that. So Vmax is approached when we have high concentration of of the substrate. So we can say that at initial substrate concentration much greater than any, constant here, what we'll have is we kind of can remove that term. And so V, which will be maximal at this point, will be equal to K2 by substrate over enzyme, of course, over substrate. Okay? So we can cancel out substrate concentration, and we know that this term right here is our V max. So we can actually just simplify this equation. So I'm going to just put here V max, right? And I'm just going to say that V max is numerically equal to whatever I substituted here, K2 by the initial enzyme concentration. Okay?